Hi guys. Well, of course, time for a video again. This time no power supply, no high frequency, no high voltage. Just a case, a beautiful case, an aluminum case. Yeah, it's time to do something else. Yeah, not always the same. But of course, in this case is not the subject of this video. This case is just, yeah, it came like that. Well, 2015, I think, I found on eBay something that I thought would be interesting for me, and I bought it. And since then, it sits in the closet, and I never even used it. What is it? Let me show you. This thing. It is called an process calibrator, well, sort of. And again, we're out of focus. I hate that. This is how it looks. It's a MASTECH MS7221, and it's called volt and milliampere calibrator. This is, yeah, it came like that. It came with some leads in the original box and with a manual. I bought it because of, at that time, I needed a calibration standard. Well, that's not a real standard. It's good, you will see it's good, but it's not a standard. And because of emotional reasons, because it reminded me what I was using in the 80s, real process calibrators costing many, many thousands. At this time, it was not euro, but shillings, a lot of money. And in no mean as fancy as that. It was really simple and mostly analog. Yeah? So, what does this thing do? Let's put that here, like that. And let's see what this thing does. So, these are the ranges. It can measure and source voltage and current. It can measure in two ranges, 100 millivolts and 10 millivolts. On the right side, you see the resolutions. That's the input. Then it can source similarly. And here you have the input and output in milliamps. And everybody that sees 0 to 20 or 0 to 24 and has to do with some process automation in the past or now, we know that this is the loop voltage, the loop current that is used from transducers to communicate analog, to send analog values back to the computers, to the host system. In the 80s, I was working in a large electronic company called AEG, and my part was to design the systems, including process automation computers and conventional industrial electronics. And of course, I was using similar things like that to test the process computers itself. But what's a process computer, at least at that time? Well, a process computer in the 80s looked like that, for example. This was the one that is not designed, I used in a large customer, in a large substation, one of the largest substations in Austria, that incorporated 110 kV, 220 kV, and 380 kV. That was a huge substation, one of the biggest ones in the middle of Austria. And it used one of these as a central processing computer. Yeah, guys, that was a computer. The power of this thing was, I don't know, I think an ESP32 has more power than that, as it was. It was absolutely state of the art at that time. It was 86, 87, 86, I think, yeah. We even had these cartridges for like hard disks. It was a combination of a cartridge and a fixed drive 25 megs, not gigs, yeah, megs, and the cartridge had additionally 25 megs. That was called Lark. It was a piece of garbage, yeah, at that time. They failed all the time, yeah. And as you can see here, we're back memory lane at the moment, but I want to show you, because many of my viewers, I think they never seen what that meant to be into the electronics and the industrial electronics in the 80s, yeah. This is the panel where I had to put the, in hexadecimal assembler, of course, the boot loader. So this thing started to boot from one of these two Larks or from another device. And this was ultra modern, because the older ones that had the series that I had before and with other customers didn't have hex input and the hexadecimal keypad. They had 16 switches here and 16 LEDs, and you had to enter the bootstrap code, not like here in hex, but in bitwise. That was a pain. And then if you didn't made an error, it started to boot, or it started to load the bootloader itself from a punch tape. Of course, this thing still has core memory. I think it is 256K core memory. It's quite modern, yeah. And it's a 16-bit computer where the CPU were 4-bit bit slice chips in series. That was the 16-bit computer, yeah? And a lot of periphery. Look how this thing looked. This is the whole power supply for this thing. Let me show you how it looks from the back. It is, let's go a little bit back. Look at that. At that time, I had to do everything by myself, yeah? All these cables, all the confectioning of these cables, all the making was done at the customer side where it is now. Here you see my soldering iron at that time, yeah. Was a lot of work. And yeah, it was pioneering stuff, guys. Today you cannot even imagine, many people cannot even imagine what that meant, yeah. All this thing on the back, this is a new backplane already. The older backplane was wire wrapped, completely wire wrapped. It was a rat nest. It was awful. If something, one of the wires burned, you had to dismantle a lot to get back. Wow. I'm not keen to go back to these times, but these were times where you learned electronics, because you didn't have anything that you help you. There was no internet. There was no PDF. There was nothing. It was just paper, books, and try and error. Look at that. That's a little bit bad. Let me show you. Perhaps you can see it better here. horizontal fans, the back of the two larks with dedicated power supply, of course. Anyway, all this looked like that. Yes, guys, that's me. 1 million years ago and a couple of kilos less. And we had these two teletypes connected with 1200 volts on the process computer. One of them was directed to the console, and the other one was connected via modem to a partner side. And it was with a blazing speed of 1200 to 110 or 1200 to 75. We used an interspeeder for that. Yeah, that's a box that makes from 1200 symmetrical RX-TX to 1275 go through the telephone line. On the other side, it is reconstructed again from 1275 volts to 1200. That was a buffering. It was blazing fast at that time. Normally we used 110 volts here. Look. And sorry if I'm bothering you with these pictures, but perhaps somebody has interest in how it looked in the 80s. This computer here, this process computer, was an 8020 16-bit from AAG, yeah, and it was connected to this system. The system consisted of 40 racks, like that, in this size, yeah. This thing was used to control the output of the commands that this thing sent on plausibility. Because if you send the wrong commands to a power switch or a disconnect switch on the 380 kilovolt system, hell get loose, yeah? So this thing was controlling everything, yeah, this system. And you see how many cards there are, digital I/O, etc. Well, at that time, nothing was software configurable. That was everything fixed in EEPROMs, and the timings, etc. Most of the timings of the cards was fixed with capacitors, RC, etc. And of course, the cards that were delivered for this customer were the wrong ones. Hundreds of cards wrong, yeah. And the solution was just to desolder a capacitor that made the RC timing too long. And of course, I did it. It took me weeks. Yeah, look at that. This was the card. And these are already caps that I have desoldered. It was I cannot say therapeutic, but it was awful. More than a week. It took me more than a week to make this card, because these cards had conformal coating on them too, of course. It was not easy. And this is how I did it. That's me. With this Philips desoldering station. I loved it. Yeah. And throwing everything on the floor as fast as possible. Whoa. These were times. This is how the system, how the control room looked. It is only the half of it. It was huge, huge. And this was state of the art, guys, yeah, at that time. This is the other side. Two monitors, graphic monitors, were graphic, that was sprites. You just made graphics from characters that you defined, sprites, yeah, awful. This is how a part of the system looked outside. Look at the cars at that time. Awful. Here you have more details. These are coils. Huge, huge coils. When you entered the substation, you felt directly that there was electricity in the air. Yeah, you heard. You were all the time, 24 hours a day. You were hearing a buzzing noise, like an angry, overloaded transformer. But you got used to it. After 1 or 2 days, you got used to it. Yeah, and in the night, when all these metal parts, you were seeing St. Elmo's fire, blue corona discharges. Was wow. And then you had this disconnect switches. First, they disconnected, of course, the load with power switches. And then they disconnected the part of the system with this disconnect. And when they did that, you had many meter-long arcs. It was beautiful in the night here. It was overwhelming, loud, beautiful, overwhelming. Yeah. And this was only because of the capacitive charge that stayed in this whole system. Yeah, look at that. And this is how the transformers looked. The transformers was the size. Is there a man there? Yeah, you can see the size. It was like a house. This is one of the transformers. There were 6 transformers, 2 for 110 kilovolt, 2 for 220, and 2 for 380 kilovolts. With the suppression coils. Look at that. And some more detail. Well, that was an excursion in back to memory lane of what I did at that time. Yeah. So let's go back to what's the video about. And the video about is about this calibrator. Will be a teardown. Details on the operation of the electronics internal, and the partially I say, reverse engineering of the digital to analog converter part, because this is of interest. So, what else do we have here? I think we can open it. This is how it looks. And first of all, before we go to the teardown, we will go to check it with a 6.5 digits multimeter. So here we have connected to the Keithley, my old Keithley 2000 that was awfully corroded on the power supply part. The analog power supply was completely, all the capacitors were leaking, traces were completely broken through the electrolyte. This thing has everything repaired. I do not understand that all these brand names, big brands, Keithley, Fluke, Tektronix, all they made the same shit. They are using linear regulators from the 78 and 79 series. That's okay, yeah, because they need the amperage and they need rather low noise, no switches. But why put the capacitors exactly even to connect to the electrolytic capacitors to connect to the regulators themselves? And the regulators are so much overloaded because of bad cooling that they burn. Yeah, they are so hot. And of course, the electrolytics, after some while, they were not even 105 degrees, they were 85 degrees. Yeah. So of course they will die. All of them made that. Yeah. Philips, the same. I don't understand that. Anyway, by the way, guys, in case that any of you has a spare enclosure that could sell it to me to a good price or whatever, this thing looks awful. It's burned. It is, I don't know, somebody did that here somewhere with a soldering iron. If it would be possible, and you have a spare faceplate or whatever of this 2000 that looks a little bit better, it's not that yellow from the cigarettes at all, I would very much appreciate if you contact me. Again, thank you in advance for that, yeah? So, anyway, we set 1 volt, let's go up to 10 volts, and you see, we have here, okay, let's do it differently. Let's zero it out, this, and put the relative. Okay, now we removed the bass noise. Let's go again. This is how it looks. We are at 1 volt, and this thing is awful to use because you cannot shift left or right to the digits. You have to go through the whole thing like that. Let me show you. If I put 1 here, you see it is 1002, and if I add 1 millivolt, it goes to 3. That means it has an offset. And it's, yeah, it is almost 2 volts or 2 millivolt offset, and that's a lot. So that means that this thing needs to be calibrated probably, but I don't have a clue how to calibrate it. So this is my second request. If any of you knows how to calibrate this thing, just please just contact me. So these are my 2 requests. In case that you have a faceplate for my Keithley 2000 and you were willing to sell it or whatever to a good price to me, and perhaps if anybody else knows how to calibrate this calibrator, please contact me. Anyway, let's go to millivolts. We are now at 0 millivolts in the second range here. And you see the offset. That means the offset we have here is 1 millivolt, 165 microvolts. Let's add 1 millivolt. Let's add, no, sorry, 1 millivolt. We are in the millivolts. Millivolts, that's microvolts, tens of microvolts. This is so complicated, this interface, I hate it. Yeah. Okay, let's go back. 1 millivolt. No, sorry. 1 millivolt. So it's at least accurate to 1 millivolt. Everything else, you see, is not okay anymore. Anyway, this is how it works. It needs calibration, but the interesting is not to show you how it works. The interesting is to show you the insides and some interesting things, how it works electronically. So let's open it. So this is how it looks open. It's a really nice build for a rather cheap unit, not rather, for a cheap unit. For a calibrator, it is cheap. The price, let's say so. It's very nice made. Let's have a look again without movement what we have here. Okay, we start from bottom to top. The input jacks and output jacks. That's protection, nothing else. Then we have here the battery connectors. 2 fuses. Absolutely nothing interesting till now. Let's turn it around. And we have the first chippies. This one is an LTO, 5-volt LTO. This is a dual D flip-flop. It's used for the on-off switch, for the soft switch. LM317 adjustable regulator again. Let's go on the right side. We have here a MOSFET, where as it is connected, it looks like it is a polarity protection on the ground side. Then we have 2 TVS diodes, 40 volt. Both of them are unipolar, so they are connected anti-parallel. Then you have a bipolar one. Yeah, this is how you can do it too. What we have here, yeah, an OP, where is it? I forgot, I lost it here. An OP297 precision op-amp. I don't know what it's doing. And then we have here, I lost everything. Yeah, LT1009, that's a 2.5 volt OK reference, let's say so. Switch mode power supply. From what I see, how the Schottky diode is connected, it's a boost, probably for the LCD. Yeah, another precision op-amp, like the first one. We are coming to the interesting things soon, because this stuff is, yeah, CPU, a Holtec, sorry to turn it around all the time, yeah, a Holtec LCD controller. I will show you for all these chips datasheets in a jiffy in a moment. Then here we have the first interesting, no, let's start with that. That's the easier one. Let me stabilize it a little bit for you. This is a dual ADC, 24-bit ADC that is used in weight scales and these things. It's, I think, a SPI with SPI connectivity, serial connectivity. Again, an op-amp. And then we have what we have here. That's a switch capacitor regulator, that it is connected to generate a negative voltage for the op-amps. I will show you all of this later. And now we have, where is the DAC? Where do we lost the DAC? I don't know where the DAC is. This is the DAC. And it doesn't make quack quack. This is a digital to analog converter, a dual 12-bit digital to analog converter. Why do they use a 24-bit ADC and only a 12-bit DAC to output the resolution? The output resolution of the current and of the voltage is less than the reading resolution. Well, not really. Look how this thing is connected. Pin 5 as we have it here, one moment. Pin 5 and 8 are the outputs of the DAC itself, of the DAC 1 and DAC 2. And they are connected in series. I will show this. I did a complete reverse engineering of this part to explain to you, because this is the interesting part of the whole teardown, yeah? And they go somewhere here to the op-amp. So, what is that doing? Well, that's a trick. This is the trick. Ooh, it's so big. This is the reverse engineering what I did. Here you have the digital to analog converter, output A and output B. And these two are combined, are summarized. So, and from the CPU side, one is used for the coarse setting and one for the fine setting. And this is how it looks. The parts here are the original part numbers of the PCB. Let me bring it a little bit closer, yeah. And you see here you have an inverting summarizing amplifier. The coarse size, what I think it is the coarse size from the logic, you have the ratio of R14 and R15 gives a very large amplification. And for the fine, that again, I think it is the fine, yeah, you have R13 with R15, that gives a much lower amplification. So I think this is the coarse, this is the fine. And this is how it looks with the inverter chip, the switch capacitor, regulator that is connected as an inverting configuration. It's 5 volt here, and we have minus 5 volt here. This is how it looks. This chip exists since ages. I use that so many times from the most different manufacturers. This one is GC, I don't know it, but it's a 7660 switch mode capacitor inverter chip, nothing else, yeah. So, but why did they do that? Why didn't they took a 20-bit amplifier? Digital to analog converter, because theoretically 2 multiplied by 12 will give you 24 bits. Yeah, blah, blah, that's theory and that doesn't work. Best case, in my opinion, and from what I read, is you get 20 to maximum 22 bits, but that's it, yeah. But let's have a look on the prices. I thought my first thought was the price. But honestly, the LTC, the one that is used in a reel, if you buy a reel of that, it will cost 10.28 euros per piece. And if you take a 20-bit, a direct 20-bit DAC, again a reel, it will cost you 11.61 euros per piece. And this is only a reel. If they buy this thing, they don't buy only one reel, yeah, they buy many more, yeah. So I'm not really sure if this was the price reason, because if you use this here, you see, you need an additional op-amp, you need additional passive parts, etc. So I cannot think that it is only the difference here, this small difference. I don't know, perhaps, but this is the only reason I can imagine at the moment. Using this technique, I do not see it very often, yeah. I will put some links in the description that explain it much better and much more thorough and much more detail. But this is the most interesting thing I've seen in this teardown. This is why I made, for this part, a reverse engineering. Well, guys, if you like my videos, if you like the content, if you like my teardowns, the designs, reverse engineerings, all of that what I'm showing to you, please press the notification button so you can get informed when I have new videos. Give me a thumbs up and please subscribe. I said that so many times, most of my viewers are non-subscribers. Guys, it doesn't cost anything. It's free, subscribing is free, and you help me a lot to move my channel further and to grow. Not me, but my channel. And I have the possibility like that to show you more interesting things. And there is more to come. You see, the variety of things that I'm having here. Anyway, let's have a look of the data sheets. Okay, let's start with the data sheets. First one, it's the Nuvoton 8-bit microcontroller, nothing special. An 8051 compatible 8-bit microcontroller. The only thing that is special in this, with this microcontroller, is that they use a PLCC packet. Why? Why do they use a PLCC packet? Probably they had millions of that on their shelves, and they used it. No other reason. Yeah. PLCC packages are used last time in the 90s. Yeah. So again, I can only imagine that they had it and they used it. Takes a lot of place, a lot of real estate. It's big, it's high, it's outdated. Anyway, it is how it is. This is the microcontroller W78E058D. That's it. Then we have the LCD controller. It's a dedicated LCD controller. They could have used, of course, a microcontroller with an integrated LCD controller, but no, that's a dedicated old LCD controller. It's not a newest one, even if it says 24. They use the HT1621. Nothing more to say. Then we have an LDO for 5 volts, probably for the logic. Then we have the switch capacitor voltage converter, the 7660. It's not a Texas Instruments that they use here. It's some Asian brand, but it's a 7660. It's a very, very versatile chip. I use it a lot during the years from different manufacturers, but it does the same. I used it for doubling, for tripling voltages, for LCD displays, and many other things. Negative, and where's negative here? Somewhere we will find it. Yeah. Where's the negative supply here? What was the first one? This one. They say it's a test circuit, but this is the negative supply. Yeah. Here you see 5 volt in, minus 5 volt out. That's it. Very, very useful chip. But not quiet. It's not noise free. Yeah. There's a little bit of noise. Then we have here a relay switch mode. It's a boost. You can use it in a boost or inverting configuration. Here they use it as a boost configuration. It's the MAX 629. This chip generates the loop voltage for the 4 to 20 milliamps mode. The loop voltage is 24 volts. That means that the generated voltage here is at least 24 volts. Yeah. Then we have, this thing is probably used too for the 10 volt generation, for the 0 to 10 volts DC output. I'm really surprised that they used this thing. And behind that, 20-bit DAC converter. Not sure about that, but I think they use it for the 10 volts too. I didn't saw anything else that they could use the 10 volts for. That generates the 10 volts. This is all. Yeah. Anyway, then we have a 2.5 volt reference. For what they use it, I don't know. Probably for the ADC or for the DAC. I think they have it integrated. We will see. Nothing special. 0.2% initial tolerance. We have then an OP297. That's a dual precision op-amp, low bias op-amp. It's a good part, good IC, but nothing really special. Again, it's quite old, 97. That's exactly the year that I received my flat, my apartment here in Vienna. Okay, let's continue. Here we have the first interesting part. That's an LTC 1446. That's a dual ray-to-rail micro power DAC. This is the DAC that they are using in a summaring. They're using both DAC outputs, and behind that they have a summary amplifier op-amp, and this is how they make probably from the two 12-bit outputs and let's say 20-bit summarized output. Yeah, interesting because it's not cheap. It's over 10 euros if you buy the whole reel, yeah, per piece. Anyway, do they have a what I see they have already here an reference, so the reference is not for that. And then we have the ADC converter. It's a dual converter again, quite slow, 10 to 80 samples per second. It's not really high, yeah, but it's not needed. Yeah, but it's a 24-bit. Again, that is not a cheap part. They have reference, okay, probably this is the reference. For that, they use the reference, but honestly, a reference, an LT1009 for a 24-bit, that's a sacrilege. Yeah, I don't know why they do it. Anyway, so these are the data sheets. Let's see the insights again. This, how we can see it here, it is absolutely not cheaply made. They use dedicated digital to analog converters, not something PWM and then a low pass filter to make a voltage out of that. No, dedicated 12-bit digital ADCs, no, sorry, DACs, but in this configuration here. So even that's an expensive chip. Look at that. It costs more than 10 euros when you buy a reel. Yeah, this is what I'm meaning. They are not using cheap parts here. The whole thing is nicely made. Yeah. Anyway, this is on the front side. There is nothing. There's just the display. This is the connector for the infrared, for the optional infrared transmitter and receiver. That would be here. Yeah, so an interesting little equipment. This kind of equipment can go very high in price, as I said before. This is a cheaper one, but very well made. So thanks for watching. I hope you liked it. See you next time. Stay safe, my friends. Cheers. Bye.